So good morning all, and let's close this. And right away, something interesting that's going on is that we coincide with exactly on time with exactly another webinar. And that one, of course, is much more real in the sense that it's Qiskit Live. They are also every Friday. They're also at 11 Central Time. And not that I'm inviting you, because they also have a recording, but it's your choice. It just came to me as a notification, so I'm taking that away for now. But what I want to go to is quantum computing, our regular class, and give you that link. In case you don't have that link, I'm giving it to you on chat here. Okay. You can always get all the recordings. Now, let me talk to everybody. Here is the link, and that link will give you everything. One of the things that it will give you is this webinar folder, but another one is the original link. Maybe we should really put it here. So at elephant scale, here, we have a place for the webinars. Okay. And that's our quantum computing webinar. Okay. So I think that I can give you that link, right? And that link, no. Oh, yes, let's see. Yes or no? I'm not sure, but that one looked right. Okay, so I better give you this link, and I will put it here on quantum computing. That is the webinar folder, but even better than this, that's the webinar announcement. So let's put it at the top. And let's say with all links. Okay, so if you ever need anything, the key link is the one that I gave you, but thank you very much. I love this reaction, very nice. Okay, and that's what we want to do today. Thank you for the thank you. But also, now let's do something practical. And that is refresh our lab setup. And no, that's what we want to do today. So that's June 23. Let's verify it is June 23. And here are the things that I want to talk about. So first of all, some announcement and something that we all guys spoke about yesterday. Last week. So I hope the sound is good enough. I see that the picture maybe is not perfect, but that's not that big of a deal. Okay, you're encouraging me, you're saying it's all good. First of all, let's look at what is it that Intel announced, then look at what is it that IBM announced, and finally, we'll do something practical, as I always do, something for you guys to do. Okay, Intel announced that you can kind of buy a quantum computer. That's not really completely true. So let's go to the announcement. And they promised to start shipping a quantum processor. As it turns out, it is not a great processor. It's Intel, it's not IBM. IBM, their processor is 433 qubits, and the most popular work that I see they're doing is on, I think it is, about 100 qubits. Intel is only offering you 12 qubit device, but that's not a joke either. And besides, it really, not that you can buy it at, Best Buy, right? Because it only goes to a few university labs right now. Well, still, that's better than all hosted in the cloud. And I try to read and understand what they're saying here. And essentially, it is to give the hardware also in the hands of the people. Because even at the university, you probably cannot build your own processor. Even a small one, you can't. So a few universities, and they are mentioned here, which universities are getting this. Well, here they are: Universities of Maryland, Rochester, Wisconsin, and Sandia National Lab. You wouldn't expect guys like Sandia already have that or do something. Okay, now there's also a discussion here that Intel is experimenting. You can't really 100% rely on them. I once worked for Intel, and I know they're people, real people, not angels, and therefore something may be not perfect. But the end result is, yes, more people will have their hands on real hardware. That's called tunnel falls. Here it's explained an interesting tidbit of information. The tunnel falls is a body of water. It's a waterfall around where some of the Intel headquarters are. So that's why they're called this way. But essentially, it is a 12-qubit processor that you can play with. And the biggest idea, I think they should continue. No, they don't. But I did read. That's not too much information. I read more somewhere. So the biggest idea is that they want the scientists to touch the hardware, not just the software, even though they do allow access to imitation. They have a simulator, and the simulator is written in C++, but you get an interface in Python and some other languages. Okay, that is the first thing. So you over there, the quantum computer enthusiasts, you can get closer to real hardware. That was number one. And so many advertisements that are very distracting. Okay. Now, whenever you have something, please say or chat, and I see that you did chat something. I'll keep it up. I want to see what you're chatting. Usually I say I cannot watch the chat at the same time as I'm talking, but that's not true. I can. So here you are, everyone. Please chat away and talk. All right. Now, the next one. So you guys asked about this, and that forced me to look at the announcement, which is great. Well, honestly, I'm gaining at least as much or maybe much more than you. Because every week I look at the news and then I do something practical. And usually I refresh the course only when I teach it. Right now, they told me I'll be teaching the course every 3 months at this large company, that I prefer not to mention, but John knows, right? And it hasn't happened yet. So this weekly meetings, they help very much with refreshing, and I'll tell you what I did. The next one is from IBM, and what they are saying is they are closer. Again, that same word. The word is not that we achieved what is called quantum supremacy. And quantum supremacy is when your quantum computer does something that regular computer, even on a cluster, cannot do. So IBM said, yes, we're getting closer. They got on the cover of Nature magazine. Where's the cover of Nature magazine? Right here. So June 15, 2023, cutting through the noise. What they're saying is this. One of the real important application that, again, is a little bit in the future is material science. And that to be very specific, is designing efficient fertilizers, building better batteries, Elon Musk's dream, and creating new medicines. All of these depend on this quantum computing algorithms, but the problem is that these quantum computers are noisy, meaning those electrons, they don't behave sometimes. And you run every algorithm quite a number of times, usually 1,000 times, 1,024 by default. So that's very expensive and unexpected for a regular programmer. He runs his program once, but quantum computing runs thousands of times. So important thing is noise. And you will just get one result more often than the other, and that will be the right result. Well, not very encouraging. And so to get into anything real, you need to compensate for noise. That's what they did. They measured the real results on the cluster. They also measured and they used the 127 qubit computer. They measured the real results on the cluster, and they measured the results on quantum computer using this Eagle process of 127 qubits. And they show something that's convincing, at least to them, that it shows promise, that they are very close to getting the real results. Well, we hear this for the last year or two, that we're getting close. And by the way, that link is here. That link is here. So you can watch this video, and it's a 1.5 minutes video. So I wonder, why don't we do this? I need to stop sharing. Then I need to share again. But this time I click on share sound. So you share it again. And why do I talk all the time? Let's listen to this. It's only 2 minutes, and see what they say.
So honestly, I was pretty nervous. We were running a really challenging experiment to explore the limits of today's quantum computers and how they compare to classical computing methods.
I try not to view this as a competition between classical and quantum computing, but I did go into this experiment expecting the supercomputer to outperform the quantum computer. So my involvement in the project was to help simulate this quantum experiment on some of the largest and most powerful supercomputers in the United States, including at the Lawrence Berkeley National Lab and the National Energy Research Scientific Computing Center.
We wanted our collaborators at UC Berkeley to use classical simulation methods to verify whether our noisy quantum processor was producing reliable results. We also wanted to push our device to limits where their methods might struggle. We didn't want them to come back to us too soon and say, yeah, we solved the problem very easily.
But using some of the novel error mitigation techniques that IBM has introduced, we actually found that the quantum device easily matched exact classical results and outperformed approximate classical results in cases where the exact answer was available. Impressively, even as we moved to circuits beyond exact classical methods, quantum still appeared to be more reliable than some of the approximate methods that we tried on these large supercomputers.
For quantum hardware, scale and noise have always been the biggest problem.
On scale, IBM's made more progress than anyone else, but noise is a different problem altogether. Quantum computers are very sensitive to noise, disturbances that cause errors in their computations. IBM has spent years developing methods for filtering the effects of noise out of quantum computations. This is called error mitigation. We were only able to do this because we've now built a quantum system of unprecedented scale and quality, and developed the ability to manipulate noise on a quantum system at the scale.
Having good, reliable 127 qubit devices with high coherence times was really a prerequisite. The hardware really enabled this project to happen.
We wanted to see if error mitigation would allow the quantum computer to even keep up with the accuracy of a classical supercomputer at this scale. With the error mitigation techniques used in this paper, we run our calculations and slowly turn up the noise. Then we extrapolate back to the zero noise solution.
how do we control and manipulate hardware at this scale is quite unprecedented. The answer to this question did not exist before.
Understanding the root cause of these discrepancies will allow us to improve both methods and is an example of the benefit of the interplay between quantum and classical. Together, we can realize a device that can solve interesting problems.
As we increase our number of qubits, reduce our error rates, and improve on these techniques, we will see a growing collection of problems where quantum computers can provide value.
Eventually, we'll reach a point where we can truly learn something new from quantum computation that we weren't able to access through classical alone. A point where we can really push at the boundaries of human knowledge.
Okay, thanks for watching. And I like how again and again we hear the same eventually. That was my big discovery. Well, I myself didn't know, are there real applications or none? Until I got onto Slack for quantum computing, and you can get to there for free and no sign up is required. That is different from becoming a Qiskit advocate. I'm kind of giving up on becoming a Qiskit advocate because they haven't replied still. Okay, that is the news that I can share with you. And now let me do something practical. Here is the practical thing that I want to do. I think the lab should mention right here. If it is not, no, it is mentioned here, okay? That's here. So if you click there, you will see that it really does open, okay? And that it is publicly accessible thing, right? Let's go down, visibility, public. All right, great. So I have brushed it up. That's what I've done. Now that is right here, right? So let us look where we are. We are in quantum computing labs. So if you clone that lab to your computer, it should work. But that's not the only thing that you should do. First of all, let's say git status. Maybe cool, maybe something new came up. No, so we're good. And now look, I'm in Qiskit environment. So I need to set up my Python in a special way. I think there is a command to describe your conda environment. And of course, as everybody else, I'm using ChatGPT. So it's bringing up my old conversations. Okay, describe conda environment. How do you do this? Well, maybe it misunderstood me. Maybe it thought describe the whole concept. No, I need a specific describe my conda environment. My specific conda environment. And it gets misspellings, that's all right. Just one command, how to do it. And tell me to list all of them. You say conda environment list. And to list type conda environment list, I think like that, right? So I have all of them, but I don't have the ready command. In any case, it's collected right here. Now I've added something that I didn't have before. That was right here, and this requirements. So it's like that. In other words, you do this. You are there. You say pip install -R. You add this for requirements, and it goes through the list and says yes. Now, I also realized that I should use all tools available. One of the available tools is PyCharm. I use Professional, as you can see. There is a community edition. So that's helpful because it recognizes the requirements. That is the requirements.txt file. So if I, let's say, install a package that I forget about, it says, oh, wait a second, your requirements are out of sync with the real world. So add this here. There are some problems, but it helps you. And that's important that somebody should help you. So that's number one. That's how I did it. I ran this environment. Then I said, Honda activate it should be spelled correctly, and I'm there. Okay, the next step that you do is, and I'm going through all of that because some of it was new to me, so maybe you will also gain by doing this. The next step that you do is Jupyter and Lab. I discovered that I didn't have a Jupyter Lab installed. I only had Notebook. So I wasn't lazy anymore because, I'll tell you why I'm not lazy anymore. Because I always go back to my advisor. By the way, that is the kind of the webinar that I'm running next, as you probably know. And yes, that's your co-pilot. That's your pair program, if you will. And it helped me a lot with quantum computing. That's why I'm talking about this. So you say Jupyter Lab. It starts the lab. By the way, please note that it starts on 8889. That's because 8888 is taken by somebody. So whoever that somebody is doesn't matter, but you can run different environments at the same time because it's careful to change the port. So here I am. Okay, so I remember that the last time I taught it, I unexpectedly encountered different errors. So it's always good to run it again. Let's close this because I need to show the whole thing. And how do you get there? You say plus, little plus here, and that's a new launcher. There was one launcher here, and that's another one. So let's say you close all and lose all. Okay? I lost all. So you say plus another launcher. Actually, you already look at one launcher. And in this launcher, you have your terminal. That is where you can do ls. By the way, it comes out back in the normal environment, base environment. Well, that doesn't bother us because we're running, and that's different notifications. We're running basically from this environment, and that environment is Qiskit. Okay, so let's look at the very first. Now, you may have run through this lab, or you may have not. And the way I did it is I used IBM course. They have the course, but they had some buts. First of all, I wanted that to run in my own environment, and with them, you run it in their environment. So some environments are very good, like Colab. Just in case, Colab is found like this, Colab Lab Research Google. That is if you want to run any Python in the world, you go and run it at their expense on their machines, and it works. So forget that, because I wanted my own, and IBM is not as stable. They are great, but they are not really working for the world like Google. Please come here and run your stuff. They do assume implicitly a little independent thinking. So I downloaded all the labs, and I think they changed it since then, and the labs were not even available anymore. I don't know where. So yes, it is a good idea to have your own copy, and that's what I did. The next step is they are wonderful labs. So you go through them like that. You either click here, and every time you click, you just read. Because this is a Python notebook, and for those who don't know, haven't used it for a while, there is text and there is code. So one way is to click here and it runs, let's say, through this text. But another way is to do Shift-Enter. That's what I just did. And you may have noticed that was a star here for a while it was importing all those packages that it needs. Now, the best practice is to put all the imports up front. Yes, that is the best practice, but practically often people import anything that they need when they need it. So it's up to you. It's here, I sometimes follow this best practice, sometimes I don't, and collect all the imports here. Okay, let's look at what we're doing here in this lab. It talks about items of computation, and what we mean is this. Somewhere there is a computer. You can submit your jobs to that computer in the cloud, to IBM's computer in the cloud, and at a very few qubits, it's all free. It's not even using your money, but it is running on a real computer. Later on, there will be labs, let me show you here, that do submit things. It's here. So if we go in there, then Shor algorithm, Grove algorithm, all these run on real hardware. Nevertheless, it's all free for you because these are running on small computers, really small configurations. But here we are running just our labs as they are, and we're running them on a simulator. A very popular approach. So if you look in here, that's air. From the air, water, I don't remember, fire, I think, elements. This is air, and you import it, and later on when you're running the simulator, you'll be running that air simulator and not the real computer. Now, the second step is somewhere there are qubits. We talk about qubits, so it's magic. To me, it's very hard to understand, and that's why I remind everybody a little bit about what's going on, is that they catch those photons, or maybe they catch those electrons. They can't catch elementary particles, and they put it in their computer. And then the particles have an amazing property. They are neither here nor there. In other words, they may be a particle, they may be a wave. So they are a particle all the time that you look at them. They are not a particle, they are a wave when you don't look at them. And what you do in your program is you describe what you want the computer to do, and then you stop looking at them. You go out, and it being a wave, it can run the algorithm. Then you come back and you say, now give me the result. I'm wanting to look at you. I'm going to look at you. Then again, you're manifesting yourself as you are looking at them. They become particles, and as such, they have either value 0 or 1. And then the result is that you can measure them and get the answer. So that's one way to explain it. And you do it with Python. So that's a wonderful manual that is explaining a lot. I'm not going through those explanations because today I'm only interested in exactly how you run it, okay? So let's do it. It explains that that's the widget, and it draws the widget. Amazing. Okay, then some exercises, and then your first quantum circuit right here. You're saying, I'm going to create a quantum circuit of 8 qubits. And corresponding to that, there will be 8 bits. So there will be 8 qubits, 8 electrons, and 8 real bits that will accept the answer. And you create it like this. Then you say, I want to measure you all and show me the result. That's the result, right? So I am not doing anything. I'm just creating them, and that's an electron or photon or anything that makes quantum computing work, but then I want to project it, I want to measure, and that's where I will get the results. Now, you could guess that the result should be all zeros, that should be 0, and that should be 0, and so on, 8 zeros, because I didn't do anything. But I want to see that, okay? So I'm drawing the initial state, I'm coming to here, and yes, I got all zeros, and I ran the experiment 200 or 300 times, as it says. And every time it came out as 0, not surprising, so that's the result. Well, add a bit more complexity, and you're doing any one of these algorithms. Now, the amazing thing, and it's still amazing to me, is that with quantum computing, you go back to such a basic level, forget the compilers, forget the clusters, forget everything you knew, and come back to logical circuits right here. Here. And we will combine our calculations out of logical circuits. So here what I'm doing is that I'm building a little quantum circuit for myself. So first you build your own computer. That's what you're doing here. Quantum circuits with 8 bits and 8 qubits. Then you're saying, I want to put, I think, 1 into last bit. The X is a negation, and negation of a 0 should become 1. So I should expect all zeros and 1 at the end. Let's draw that. Let's look at the result. Where are we? And the result is 1 on the very left side. Indeed, it was all zeros, and now it's 1. Well, it seems extremely simple, but I know we get a promise. Eventually, you'll get to more complicated algorithm, the real one. But bear with me, go through this lab. And if you are not doing it now, you can live with it later, because you're mostly interested in mechanics of it. And as you're doing the mechanics, you will also learn a little bit about setup, because nothing is easy. And even setting this up will require some debugging. So first of all, we're doing some additional circuits. For example, this is X C naught, right? So negate, and not only negate, but make it based on the other qubit. So negate when that qubit is 1, don't negate when it is 0, and we're getting into more complicated circuits. You will read that. If you want to follow, you will read that. Again, what I'm interested is that it should run all together. Reading, understanding, that's up to humans. Running, that's, we are doing this. So that already represents a little bit more interesting and more involved legal circuit, and it still works. And just to verify, these are the versions. Okay, so I see one little question. Let's look. Very cool, says Michael. Yes, I agree that's really awesome, cool, especially because you can later on do it. And if something doesn't work, well, email me. Okay. Yes. So how do I don't know how to put the reaction here, but anyway, thank you. Now, what I want to show you just one more lab, and how you proceed to the next step. And the next step is debugging when it doesn't work. Not so much the quantum computing step, but programming step. So we all realize by now that there is magic computer somewhere. We all realize that we don't want to trouble it for little things. So we can do a simulator, and that's what we brought in. We imported the simulator. Okay, but let's look at the next lab. The next lab in the very first chapter is representing qubit states. Okay, representing qubit states, and it's talking about that. So far we said our qubits will be 0 or 1. But we want something more interesting. We want either 0 or 1. We want to put it in a special state where we don't watch it, let it play, and come back and measure the results. That's what that lab will be about. So you start running it, and it explains that you are now going into the world of quantum bits, and explains how it can have a state. Well, it's a wave. As a wave, it has various densities in different places. The end result of it is you can think of various densities as probabilities. And so you get a real qubit that could be 0, could be 1, and it can be anything in between in the sense of probabilities. And that's what you create here, right? So if so, I see a comment. Yeah, computer, right. And I want to just run a little bit. Again, I'm building little computers, but I want to come to the place where we're becoming real here. So what we're doing here, we're creating our little computer, and then we initialize it to a state, but then we want to transpile the circuit for the simulator. That's where you get an error. At least initially I got an error, because what you want is you want what's called superposition. You want not 0, not 1, but in this case, 0 with probability of 0 and 1 with the probability of 1, and that the complex part of this number is representing the other part of the probability. But I'm not interested again in what it's doing. I'm interested in the fact that it doesn't work. And for that, previously, I would struggle with all the problems and versions of that. Now, but yesterday when I was preparing and it gave me an error, I simply copy-pasted that error into ChatGPT. I erased it, all of that, but we will come to an error. So, and it says, oh, you're using Qiskit, because remember, it knows everything. And that looks like an outdated version. You're getting an error. That's how we should fix it. Now, that's what you would initially do with Google, right? You would find, did anybody have a problem like I did? And instead you get the answer. So let's look, that one I fixed. So that code is not exactly what was found in this notebook, but it's better because it works. And it stopped working just because they upgraded the package. So that brings us back to the need of this requirements. The best practice is to do not what I did. The best practice, you need to mention Qiskit and also the version. That's saying at this version it worked, and in every next version it should. If there are any problems, you will discover it here. So again, that's not the best practice. I should put the versions, and that command that I wanted to show you that describes your environment will give you the version. So that's what you would put here. Okay, that's why it stopped working. Nobody was dishonest. It used to work, not anymore. Then what you do is you run to here and you find out that, boom, it doesn't work. All right. I told you I'm not such a great programmer in that. And besides, that really is a Python problem and not quantum computing problem. So that's what you do. Just straight like that, whole thing, no explanations, because ChatGPT knows what you expect. Let's see. Okay, so it's talking about that that you are using deprecated method. And there will be two basic approaches: change the code or change the library. Starting from Qiskit Air 090, you should use different ways of doing things. So you have two ways. For a quick fix, you can go back to Qiskit before 090. Or, which of course is preferred, you can verify why is it that you have the wrong version of Qiskit and install it, and then it will run. Okay, so it says before, after. Well, let's try that. We need to find, well, I am already using transpile, so I'm not going to debug it in front of you and waste your time, but basically that's how we do. So that changed the whole thing. That's where QC, quantum computing, and ChatGPT come together, because one helps the other. And I fixed the previous error, and a bit later I'll fix that too. Well, that's the very cool way of doing things, and that's why I became much bolder. So back to the question of, will the ChatGPT kill us all, or will it be very helpful? And that's, there are two camps in the world. I always see the proof that it will be very helpful. I'm not sure about killing us all, that's another story, but helpful it is. And that is the discussion that I'm having continued in the next webinar, the ChatGPT webinar, where I'm implementing it in a legal system, and the lawyers who now are convinced that they are, it's a game changer completely. Okay, they are into it. So these lawyers, they say that it will first kill us all, but really it's a great help. Well, that's my story also. Yeah. Okay, that's it. That's it for the quantum computing. What I expect you to do is, guys, really try to play with these labs. So if I now say that here is our quantum computing, okay, and make a copy of that. Then that will be next Friday. That's the plan at least. That all we did. And now recommended task. Okay. Now, what I will do is fix all the and make them work. But I'll put one little word, almost all of the labs, because I can't all. You see, it's everywhere, this AI. No, I like what I said. All right, and maybe something else will be added, but that's for our next conversation. Yes, thank you, Lawrence. That is a great tool. And guys, that's it for today. But if you have anything, here is my email. Okay, here's my LinkedIn, connect. Here is the list of all webinars. And then all of that information that if you missed it, then it's all here, and you can just look through what we did. We always put a link at what we do and what the story is. All right, so thank you very much, and I see you soon, maybe at the next one, but if I don't, then have a very good week. and you will get the recording. And Sean, by the way, we have our story going on, but we'll figure it out. Well, I'll tell you very shortly that this cup, that by the way, I'm offering to everybody. You remember my cup? Well, that impressed me when one of the kids had the cups. Had the cup, so I got the cup. Now I'm honestly offering it to you guys as a present because you're great guys. And I sent it to one of you, and it came broke. Oh no, too bad. So I wrote to the guys who shipped it if they can, well, replace it for free. But if they cannot, I will still ship another one. Okay. All right. All the best, guys. Goodbye.